the format. So we will have, right, there'll be the talk, and then there will be public questions, and then everyone but the candidate and committee will leave the virtual room, so some further grilling can happen, and then the committee will deliberate, and then and then notify Abe of what it decides. So. All right, so let's get started. Abe is going to tell us about quantum Monte Carlo calculations of scattering.
All right, thank you, Ken. Thank you all for joining me here today for my dissertation defense. It really means a lot to see all of you here today. So let's get into it. The fundamentals. Ab initio calculations of nuclear collisions. What do I mean by ab initio? I just mean starting from the bare interactions between neutrons and protons and treating them as fundamental particles, even though we know they are composite particles. So why do we want to do this? Well, we want a predictive theory of all nuclei. We want to be able to predict low energy cross sections, and when we're doing these, we want to avoid system specific models. Now, collision problems are generally significantly harder to treat than comparable bound state calculations, and usually this means that there's only been a few ab initio nuclear collision calculations done so far. So in order to do these calculations, we need accurate 2 and 3 nucleon interactions. We need to be able to solve the many-body Schrodinger equation, and quantum Monte Carlo has been successful for bound states up to carbon 12, and it's quite useful for dealing with hardcore potentials. So we think it's a pretty good starting point to solve these problems. Now, what we hope to get out of them is a unified treatment of collisions and bound states, and be able to quantify our uncertainty for our choice of nucleon interaction, and then hopefully feed back those results into the models that actually make them possible and improve them. And then we can obviously apply this to some astrophysical models where experimental results might be difficult or impossible to measure. So we're actually solving the many-body Schrodinger equation, which is just an eigenvalue problem where the Hamiltonian is operating on the wave function, which is a function of particle positions, total angular momentum and parity, isospin, and isospin projection, which is really just a representation of the imbalance of neutrons and protons in the system, and then gives us back the total energy of the system. Now the Hamiltonian is just the sum of the kinetic and the 2 and 3 body potential that I was talking about earlier. And then for scattering problems, we have a additional boundary condition that requires a little bit more thought than the bound case. Now these nuclear potentials, I really just want to talk about two main frameworks today. So there is the first one I want to talk about is the phenomenologically organized potentials. And for quantum Monte Carlo methods, we usually use the argon V18 2 nucleon interaction in combination with the Urbana or Illinois family of 3 nucleon potentials. Now you'll see most of my results today as used with the argon V18, but we also use the more modern chiral potentials. This is really just an application of chiral perturbation theory to these nuclear interactions. And then what I want to just emphasize is that when these models were first being developed, they were extremely non-local in coordinate space. So they were developed in momentum space, and they were really unfriendly to methods that required a potential that's diagonal in R space. And so that's what motivated the Darmstadt and Norfolk potentials to really be able to be used in these quantum Monte Carlo methods that require a potential that's local in coordinate space. And so you'll see some of my calculations done with these also. And then it's also useful to understand the experimental setup in order to get a really good grasp of what's going on so that we can actually translate our theoretical results to the experimental calculations. So what's going on in the lab is that we generally have a monochromatic source that gets narrowed, and in our case, in all my results, it'll just be a neutron beam. And then it interacts with the target, and then you'll see it either be a tritium or an alpha particle, and then the neutrons scatter off and get picked up by the detector. Now this detector will just count the neutrons, and then it'll get a estimate for the differential cross section. And then if we move this detector around the lab, we can map out that differential cross section, and then integrate over all angles to get the total cross section. And this is how we relate theoretical results to experimental results, are these cross sections. Now, these cross sections are also spin dependent, so you can imagine if the neutron comes in spin down, it might get scattered off and picked up at the detector when it's spin up. Now, this is a property of the nuclear interaction that goes on. and can happen in some cases. And when this happens, when it gets spin flipped, this is a more difficult case to compute. It's what we call coupled channel problems. And so we have to, a little bit more care has to go into the calculation. And we'll see that come up again later. So in order to relate to experimental results, we have to be able to compute that cross section. And so we need a little bit of formalism to get there. And so we start with the asymptotic form of the wave function. So this is just when our projectile and our target, that is the neutron and triton, get infinitely far apart. We can write the wave function as this sum of the f and g functions, which are just linearly independent functions. You can really just think of them as sines and cosines. And they have some amplitude A and B. And if we have to do a couple channel problems, we have to sum over all channels. So we need multiple solutions to be able to solve this problem. Now, once we have those amplitudes, we can compute what is called the K-matrix, and the K-matrix encodes the scattering information, but you might be more familiar with the T and S matrix, which are pretty much very similar, just slightly different, and they all can be translated from one another. And so once you have the amplitudes, you can get the scattering, whatever matrix you care about, and then get the scattering observable right after that you care about. Now, what I really want to emphasize is that once you compute these surface amplitudes, you immediately have whatever scattering observable you want. And so the really main goal is to just compute these surface amplitudes. So in order to do that, we need a wave function. And the first part of that journey in generating the wave function is variational Monte Carlo for us. So I got to tell you a little bit how we do that. Well, the VMC wave function is really just a position-dependent spin isospin column vector with components based off the number of neutrons and protons in the system. Now, the form of the wave function is really just a product of operator correlations acting on the Jastrow wave function, and these operators are really just the same ones that were in the 2 and 3 body nuclear interaction that you saw before. Now, the Jastrow is just a product of scalar correlations, which are functions of the separations of pairs and triplets of particles, multiplying a orbital spin isospin structure that's a sort of Slater determinant-like form based off specified quantum numbers. And there are multiple ways of organizing those quantum numbers, and they each have their own weight beta. Now, what I want to emphasize is that at each point of the variational wave function, there are tunable parameters, quite a lot actually. And so we optimize those parameters by minimizing the energy. That is, we can compute the expectation value according to this integral, and based off the Rayleigh-Ritz variational principle, it always guarantees a upper bound to the true ground state energy. And so that's how we optimize our parameters, by minimizing the energy. And so after this process, what we're left with is a good approximate for the wave function for the quantum numbers that we specified. So how do we actually go about adapting this wave function to scattering states? We want to apply the true scattering boundary condition that you saw before, but VMC needs an eigenvalue problem. So we take our particles, we trap them in a box, and then along the surface of that box, we apply a log derivative boundary condition, and then match smoothly in order to get the true boundary condition. So whenever you see this zeta here, just think boundary condition at the surface of the box. And so once we apply that boundary condition, it immediately specifies an energy of the system. And so that energy we get exactly the same way. We optimize the parameters, minimize the energy, and then with that energy and boundary condition, we can get a phase shift. And that phase shift directly tells us the scattering information of the system. But you can also do it by computing those surface amplitudes to get the phase shift. So that's what I've been up to, is figuring out how to compute those surface amplitudes. Now, being able to do that in VMC requires a lot of work and thought, and so we'll go into it. But what I want to emphasize is that when you're doing these coupled channel problems, you really do have to compute the surface amplitudes. And so in VMC, if you just think, okay, we can just read off the surface amplitudes of the wave function at the surface, you run into a lot of trouble, because outside the strong interaction region, the VMC wave function isn't that good. And so near the surface, you run into a lot of problems of the VMC wave function because there's limited options to optimize the wave function out there. And generally, we've been pretty bad and not really clever at getting a VMC ansatz that's good at collectivity. That is when there's really separate clusters, so a separate neutron triton. The wave function isn't good at predicting what what that actually looks like. And this generally, these many body methods, it's a common symptom to have incorrect wave function tails. And so what we'd like is a method to compute those surface amplitudes that take advantage of our accurate interior wave function. And so that's what we call the integral method actually does. Has quite a long history in the literature, but you really just start off with the Wronskian and the Green theorem of those f and g functions, and then if you work this out, you can immediately get the surface amplitudes a and b. Now, the one thing I want to note is that for the true wave function, these two integrals will cancel out, and we use that as an approximation in our calculations. And so all you're left with after that is just computing this single integral for each of the surface amplitudes. Now, you also immediately run into problems when you try to calculate the Hamiltonian, when you evaluate the Hamiltonian operating on the irregular Coulomb function. So it's irregular because it diverges at the origin. If you evaluate the Hamiltonian, you're just going to essentially be evaluating the Laplacian on that irregular function. It's going to pull out a delta function, and then that delta function in the integrals is going to pull out the wave function at the origin. Now, you could compute this in VMC, but it would require substantial rework of the code. And essentially, right now how it's set up, you would have to sample a infinitely small space in the wave function. So the probability that you're going to sample that is extremely small. So your variance in that calculation is going to be quite large. In the current way we have the code set up. So the way we go about solving this problem is to just regularize that irregular function. So we just make it go to 0 at 0 cluster separation, and then when we get to the surface, we just have it give back the irregular function. So the general form shouldn't matter all that much, but this is the one we used. We did check other choices, but they didn't work as well in our validation tests, and I'll have more detail on this later. But moving on, you can just apply the you can apply the regularizer and then check that this relationship holds at the surface of the box, and then immediately get out the surface amplitudes, A and B. Now, diving into a little bit more detail what those integrals actually looked like, all I really want you to focus on is this term right here, VREL minus VCC. Now, this VREL is the actual potential between particles in one cluster and particles in the other. That is, it's the interaction between, if we just had particle 1 being the neutron, it's going to interact with all of the particles in the triton. And then the VCC is just the Coulomb potential between those in those same terms. Now, as the neutron and triton are going to get farther and farther apart, the nuclear potential is going to fall off really fast. That is, the strong nuclear force going to fall off really fast, and all that's going to be left in this term is the Coulomb potential. So as you can see, this term is going to fall to 0 quite quickly outside the strong force. And so essentially what's going on is that the dominant terms in these integrals are going to be dominated by the short range interaction of the short range interaction. And so what's really nice is that you don't really need an accurate wave function outside the strong interaction region. And so VMC not being accurate near the surface really doesn't matter all that much for these integrals, and so you can get a lot better results out of them. And then additionally, it's going to fold in more physical information based from the potential rather than just computing the wave function. Additionally, when we were doing these calculations, we had remembered that in bound state cases, evaluating these integrals, you could get really good results if you just use the experimental energies inside these integrals instead of using the quantum Monte Carlo calculated energies. And so what that boils down to is the fact that we noticed the actual wave function didn't really change very much with energy. And so a lot of the energy dependence in these surface amplitudes was largely from these F and G Coulomb functions. And so the approximation we came up with is if you just take one boundary condition, optimize your energy, get a wave function, and then just vary the energy inside those F and G functions. That is vary the inside the red squares here, vary the energy inside those functions. You can map out the energy dependence of the scattering system. And so what this is really nice is it drastically reduced the computational effort necessary to do that. And this used to be human and computational effort, but I really put in a substantial amount of work to fully automate the optimization process completely. So now it's just a couple of buttons and you can get a new wave function for whatever potential or boundary condition you implement. Now, additionally, like I said before, you need multiple solutions to be able to compute coupled channel problems. That is, you have to choose a boundary condition for one wave function, get an energy. You have to change the boundary condition and make sure that the second wave function is linearly independent with the first, and then hope that you get back the same energy as the first one. And so this directly allows us to compute the surface amplitudes at the same energy for two wave functions we know that are linearly independent. So it solved that problem quite nicely. But how do we actually verify that the integral method is working as intended? So we do that with by computing what are called spectroscopic overlaps. So it's really just a projection of the full scattering wave function onto the cluster product space. And so for the neutron triton case, it's the product of the full H4 wave function onto neutron triton space. And it has its definition from this integral, but we can also do the integral method. That is, this A bar and B bar are really just general form of the surface amplitudes just for any cluster separation. And so actually carrying out those integrals, we can compute the spectroscopic overlap as a function of neutron triton cluster separation. That is the separation between center of mass between the neutron and triton for a specific case in neutron triton scattering. So looking at the first case, that is the calculation by definition in the dashed line. So we chose a boundary condition, minimize our energy, and this is the energy we got in MEV. And then we want to compare it to the dashed dot line. That's the same wave function, same boundary condition, just computing with the integral method. And we have quite good agreement below 5 Fermi. So that's indicating that our wave function is good and that no matter which method we choose to compute these overlaps, they're computing the exact same result. So indicating that the integral method is working as intended. Now, the next thing we had to do is check that the fixed interior wave was working. So the way we did that is we take a new boundary condition, then optimize our parameters, minimize the energy, and that's the energy you see here, the 7.34 MeV, and that's the dotted line here in black. Now, the fixed interior wave says that we can take the original wave function and then just change the energy inside those F and G functions to match the energy here. And that's exactly what the solid black line is. And then indicating that the fact that they're nearly identical in this case tells us that the fixed interior wave is able to compute scattering observables at energies that isn't specified by the boundary condition, which is quite useful because that means we can get a lot more information out of our wave function as indicated by this blue-green coloration, because it's the each one of these lines is an integral calculated with just using the single wave function here at the center. Now, like I said before, we got to actually take a little bit more care about selecting the regularizer. Now, this exact form was made popular by the hyperspherical harmonics group, but for VMC, it requires a little bit of additional thought on how to choose this choice. This choice of gamma can bias our results. We got to be careful in how we do that. So for at least for all methods, gamma below 0.25 inverse Fermi, the Wronskian of those F and G terms are going to fail at the surface. And then for VMC above 1.25, the regularizer doesn't really remove the singularity of that irregular Coulomb function. And so there needs to be a sweet spot in there, and then we need to be able to identify a regularizer that does not bias our results. So in order to do that, we went back to our trusty spectroscopic overlaps. That's what you have here. The dashed black line is the calculation by definition that we trust inside phi Fermi, and then the coloration that you see here is that integral method, but we've changed the gamma. And so we need to be able to estimate our agreement between them, which is what we do is we just take the difference between them, sum it up and square. That's what this SSE, the sum of square errors, is doing. And so what it's really doing is representing the agreement between the calculation by definition and the integral method. And so we want to minimize this error and maximize the agreement. And so we know that in the stable region here, we're just going to choose the gamma that makes it so we best agree with the calculation by definition. And those are the regularizers that we have on the left. And so with that choice taken care of, we can move on to actually computing scattering observables. These are phase shifts as a function of neutron energies for the uncoupled channels in neutron triton scattering. Now, this solid black line is the R matrix calculation. It's a really good experimental fit to data. But I want you to think of it as a landmark as we move from figure to figure. It's really just there to make sure that we're in the right ballpark. Now, the hyperspherical harmonics case are these black squares. For these smaller systems, we can treat them as nearly exact results. And so the closer we are to these black squares, the better we're doing. And so the first calculation that I want to show you is the direct method. That is, we just chose our boundary condition, optimized our parameters, got an energy, and then used the energy and boundary condition to compute a phase shift. And then overall, the direct method with variational Monte Carlo doesn't do very well. And then the integral method is the
أنا أني بزوم كان زي كاخذ زي شاطع يشلي بو زي PhD defense باي
then the integral method is the cyan squares, where it improves on the direct method a decent amount. And then lastly, the red the solid red curve is the fixed interior wave, where we used a wave function near the center of energy range. And overall, the fixed interior wave does a pretty good job at predicting the phase shifts across the entire energy range. For the S wave, for the P wave, the fixed interior wave falls short below energies that was for the wave function that was used. And overall, in the P wave, the direct method falls short. And then additionally, the integral method improves. And so overall, we think the integral method and the fixed interior wave is doing its job and predicting better phase shifts than the direct method. So we can move on from there and actually calculate with other nuclear potentials using the fixed interior wave. And that's what we have here for those uncoupled channels. So in red and blue, we have the argon V18 and the Urbana 9 phenomenologically organized potentials in comparison to the more modern chiral potentials with and without three-body interaction. Now for the S wave, it's mostly determined by the node in the wave function, and so they're all very similar. And so not a lot of interesting things are going on in this figure, but as we get closer to zero energy, a lot more interesting stuff goes on. Now in the P wave, the one thing of note is that the Norfolk interactions are just a little bit stronger, more attractive than the phenomenologically organized potentials. And we'll see that come up again later in the coupled channels. So these are the first few relevant coupled channel cases for neutron triton scattering, where each column is a coupled channel case. And so the first column being S wave coupled to D waves, where this mixing parameter tells us generally how mixed or how coupled the channels are. And so just like before, the S wave is mostly determined by that node that's in the wave function. And so not too much is going on there. What I really want to talk about is the more strongly coupled case of the spin coupling of in the 1 minus, the singlet and the triplet P wave are coupled. We do a pretty good job in the triplet case, but in the singlet case, we're way off. And so we think we can improve if we just get better wave functions. But really what we think is failing is that the fact that these two wave functions that we generated are failing the linearly independence test that we need to be able to compute these observables. So bringing all of those together, we can compute the total cross section. And so as a function of neutron energies, that's what we have here. Where the first thing I want to point out or talk about is the relationship or the difference between our calculations in red here and the hyperspherical harmonics case. They were both using the same potential. We see that the VMC results don't quite meet our expectations. And so what this is really indicating is that most likely the fixed interior wave shouldn't really be used outside of 1 MeV of the wave function that generated it, and that we can also improve these results if we get better wave functions. Now, additionally, we see that there's a stronger attraction using the Norfolk interactions, and this is mostly due to those P waves, and that shows up as a broader resonance feature in the figure on the right. So how do we actually go about getting better wave functions to improve these results? And that's what Green's function Monte Carlo is all about, is generating better wave functions. Now, we can get scattering observables for single channel just fine by, right, we can get energies with GFMC previously. But what I want to show you today here is that I actually carried out the integral method using GFMC wave functions. Okay, so in order to do that, I gotta tell you what GFMC is actually up to. And we start with the time-dependent Schrodinger equation. That is, changes in our wave function is really equivalent to changes, the equivalent to the Hamiltonian operating on the wave function at that time, which has a general solution of a time evolution operator acting on our initial wave function. Now, doing something a little bit funky, we're going to do a change of variable to imaginary time. That is tau equals IT, and that operator then becomes an imaginary time evolution operator acting on our initial wave function. And to see why that's useful, well, we can think of our wave function as a sum of eigenfunctions and eigenvalues of the Hamiltonian. Where if we took that operator and acted on those basis states, it's going to pull out a exponential decay operator with where the E is the eigenvalue for that state. And you might immediately see where this is going. But if we take the limit of imaginary time to infinity, it's the high energy states are really going to go away quite quickly and get killed off. And so the term that's going to be dominated in the sum is going to be the lowest energy, which is going to be the ground state. And so that's what GFMC is up to. It's a way of projecting out the ground state by taking this limit. If we can write this operator out and then be able to apply it to our initial wave function, where in our case, this initial wave function is going to be the variational Monte Carlo wave function. And so, unfortunately, the propagator is quite unreasonable to compute for any arbitrary tau, but we can do a pretty good job for small changes in imaginary time. So that's what we do. We do a bunch of little steps, but we do a lot of them. And so that small time evolution operator can then be written as a integral over a Green's function acting on our wave function, where here I've left out the spin isospin indices. Now, once we have this operator, we can then evolve our wave functions in steps of those small time steps based off this integral. And then that integral at the final time step where we think we've converged, it's really just an integral of the Green's function acting on the wave function at the previous time step. But that wave function at that point is an integral of the Green's function acting on the wave function from the step before it, and then so on until you get back to the initial wave function. And that's what these red circles here are. And then we propagate forward in time, and we end up at these orange circles, which is then the line there is the integral in front of it. And so as you move through in imaginary time, each sample that we initially started with in VMC then becomes what we call a walker. And then as we're walking through imaginary time, the specific sample that gets done is going to then become a sample for the integral at that imaginary time. So as the walker goes through, we're taking samples of the integrals in the chain. In the end, once we've gone through enough imaginary time, that is, we've taken the limit enough, we end at the final state and we're able to actually evaluate the propagated wave function. And so we use that propagated wave function in combination with the VMC wave function to compute observables. And so in order to compute those expectation values, well, ideally what we'd like is the propagated wave function on both the left and on the right in this expectation value. But if our wave function is really just samples in configuration space, when we propagate the wave function on the left, it's going to be at different points in configuration space than the wave function propagated on the right. And so we can't really carry out this integral. You also run into problems if there's derivatives in this operator, because if you can't really take the derivative of something that's just samples in configuration space. So what we're left with is we have to compute what are called the mixed estimates. Now, it'll be important what side the VMC wave function is on later, but currently you can just think of them as this form here, where the propagated estimate for the expectation value for the operator that you care about is really just 2 times the mixed estimate minus the VMC result. Now there's a special case that I want to show you. It's the energy expectation value. And this is special because the Hamiltonian commutes with the propagator. So we can just think of the propagator moving half of the propagator past the Hamiltonian and operating on the left side half, and then the other half is operating on the right. And so we're able to actually compute the true ground state energy. Now, in practice, what we do is we take the limit. So for any sufficiently large tau, that is, we've propagated enough steps, the energy should stabilize to the true ground state energy. And we can see that if we just look at the alpha particle expectation value of the energy as a function of imaginary time. And then starting from our VMC result here in the blue band, and then the black circles are the energy expectation values as we're stepping through an imaginary time. And then what we see is that immediately the high energy garbage in the VMC wave function goes away quite quickly, and then it stabilizes, and we're able to block average these energies to compute the expectation value for helium-4 in this case. Okay, and this has been done quite a lot for GFMC. For bound and excited states, what we have here is a plot of absolute energies for each of these states, and on the left in blue we have the phenomenologically organized potentials, and then on the right in red we have the chiral potentials. And then when they align with the middle, the experimental results, that's when they're in pretty good agreement. Now, GFMC does pretty good. We think we're about 1 to 2% for these energy calculations, which is pretty good for nuclear physics, but for electronic structure, I know it would be quite terrible. But in the end, we think we're doing pretty good, and which is why we think GFMC is going to be a really good starting point for these scattering calculations. So how do we actually do scattering in GFMC? Well, just like VMC, we want to apply that true scattering boundary condition, but GFMC needs an eigenvalue problem. So just like VMC, we apply that log derivative boundary condition on the surface. But unlike VMC, where we could just explicitly insert the boundary condition, in GFMC we have to enforce our boundary condition by method of images. This is the same method of images that shows up in your introductory E&M courses. And so to show you what's going on, I want you to view that particle in a box. So this is the box that you just saw, as really a short range part of the wave function that fills all of space. And so as the walkers are going through, they're going to receive contributions from both inside the box and outside the box. And so how do we go about computing those outside contributions? Well, it's the method of images. And so we do that with a simple change of variables to map the outside to the inside. And the best way to explain the method of images is as we're walking through the box, we are going to have image points that walk along the outside of the box. And then when we get near the surface, we're going to pick up image contributions. And so we just apply that log derivative boundary condition to linearly extrapolate to get the wave function at the just outside the surface of the box. And that's how we enforce that boundary condition zeta. And so once we can apply that boundary condition, it immediately specifies an energy, like I said before. So just like VMC, we get that energy, and then propagating the wave function in imaginary time, the scattering wave function energy is immediately specified by that boundary condition. Now, to show you that we really can specify an energy, I have here a plot of multiple boundary conditions. That is, each blue and red line pair is a different boundary condition. So, so once we specified one boundary condition, it immediately specifies the energy. And as you can see, we are quite stabilized for each choice of the boundary condition. Okay, so once we have those energies and those boundary conditions, like I've shown you before, we get a phase shift. But what I'm really excited about is computing the surface amplitudes in order to get the scattering information, because we think they're pretty good and they're necessary to do coupled channels. Okay, so how do we get those propagated estimates for the surface amplitudes? Well, ideally, we would want the propagated wave function and the propagated channel cluster wave function, but like I said before, you couldn't carry out those integrals. So what we're left with in practice is to compute what I call the left and right mixed estimates. That is, for the left, we have the propagated target. That is inside these channel cluster functions. There's the target tritium or helium-4. And those are the GFMC propagated wave functions. And then for the right estimates, we have the full A-body propagated scattering wave function. And then once we can compute those mixed estimates, we're able to get the first order accurate surface amplitudes A and B after we've taken care of the norms, of course. Now, what I want to emphasize is that for the right terms, we needed to be able to compute the potential onto the channel cluster functions, which required a significant overhaul of the code to be able to do that. And so additionally, when we were setting this up, we also realized that all the neutron triton channels were not implemented in GFMC. So in order to decouple the new feature implementation in the code, we decided to test the integral method on neutron alpha scattering, which was also previously benchmarked with GFMC results, so it lined up nicely to make sure that we were doing everything correctly. Okay, so how do we actually verify that the integral method is working in GFMC? Well, we go back to our trusty spectroscopic overlaps. So the original way the GFMC spectroscopic overlaps were originally implemented by Ivan Brita back in 2011, where he set up a lot of the code and framework to be able to calculate these special kind of off-diagonal mixed estimates. Now it was just my job to figure out how to apply the potential to these channel cluster functions. So did that, and we can immediately compute the integral method spectroscopic overlaps, where these A bar and B bar, like I said before, are the generalized form of the surface amplitudes just for any cluster separation, but now they become mixed estimates where we got to compute the propagated form of them. So actually carrying out those integrals, that's what we have here for neutron alpha scattering, where the Rn alpha is really just the neutron alpha cluster separation. And then what we have here in red are the GFMC results, and blue are the VMC results. Now the scatter plot, the circles are the direct calculation by definition, and the solid lines are the integral method calculations. Now for all the methods, there's really good agreement below 4 Fermi, indicating that the wave function is good and that the integral method is working as intended. So we're quite happy with that as an indication that the method's working. Okay, so moving on to the P waves, we have on the left the 1/2 minus and on the right the 3/2 minus. Now there's a much sharper disagreement after about 2.5 Fermi for each case. Now there's quite a lot going on here, but what we think is going on is that the fact that the VMC and GFMC wave function is struggling at that collectivity. And so it's really struggling to get the cluster, the neutron alpha clusterization correct. There's also additional features going on because the propagator requires local interactions. So we really had to project our potential down to a local version of it. And so there's additional approximations that go on there. So we really need to be a little bit further investigation to check that these differences are really a significant correction coming from the integral method. But that can be done quite easily. And so with those results, we're quite happy that the methods are agreeing within at least 2.5 Fermi, because it's indicating that the integral method is working in that really strong interaction region. Okay, so actually verifying that our results work properly, or that the method is working, we go on to computing scattering observables. So what we have here are phase shifts in the 1/2 minus P wave for neutron alpha scattering as a function of center of mass energy. Now there's a lot going on, but one at a time. Then we have the direct method using VMC wave functions. That's these blue circles. Overall does quite poor in comparison to our previously calculated GFMC calculations. Those were done in 2007, and we think they're pretty accurate representation of the phase shifts in the system. Then the next thing you can do is the integral method using those same wave functions. They improve quite a lot on the direct method, but don't get us all the way there. We still need the more accurate GFMC wave functions, and then that's what the red circles are. They get us a reasonably further away. They're the GFMC energies and that boundary condition we specified. And then applying the integral method to those wave functions, we see we get all the way there. We match right onto our benchmarks. Now, additionally, we can also compute the fixed interior wave using a wave function that was computed near the center, near the energy at the center of this system. And so what we see is that the VMC fixed interior wave does a pretty good job at following the trend of the integral method, but the GFMC fixed interior wave does not. And so I was disappointed in that, but what I came up with is a interpolation scheme that should fix it. So it uses the fixed interior wave to interpolate between these two wave functions, and so it allows us to get more accurate results, essentially over the entire energy range, but still being computationally efficient. And the last thing is the solid lines are a fit to the integral method. Okay, so moving on to the S wave, we have the same thing. The direct VMC results are quite poor, but then it gets improved a lot by the integral method. And then in comparison to the GFMC results, the GFMC direct method matches quite well with our previous calculations of the in 2007, and the integral method, but at least below 3 MeV, matches quite smoothly onto those calculations as well. There's only a slight disagreement between the two phase shifts after about 4 MeV. And then lastly, we have our most interesting case because there is a strong resonance feature in the 3/2 minus. So looking at this system, we see the exact same thing. The direct VMC results are quite poor. The integral method improves in those VMC results. The direct method remains consistent with our previously calculated direct GFMC results. And then the integral method does a reasonable job, but struggles near the strong resonance feature. So I think what's going on here is there's a little bit more care can go into these calculations. So I think we can improve them by improving the VMC wave functions, because the VMC wave functions are just as important in these GFMC calculations. So when we improve them, we should get better results. And so what's really happening is that near the strong resonance, if we look at the K matrix, which is the tangent of the phase shifts on that same energy range, we see the strong resonance show up. And so the large error bars here are really representative of, we're measuring that A surface amplitude. That A is going to 0, but we have consistent Monte Carlo sampling error. So delta A over A is going to blow up near this resonance. And we see the same thing with the VMC wave function. So I think if we can improve the wave functions near this resonance, we can get results that match right onto our benchmark. Now, in summary, what I've been up to these last few years is I have applied the integral relations to calculations of phase shifts and scattering observables to the full quantum Monte Carlo context, and I verified that the integral method was working as intended by computing spectroscopic overlaps by definition and with the integral relations, and I demonstrated a valid option for computing coupled channels in quantum Monte Carlo, and I developed overall a code base that's streamlined and has the framework to be able to use these calculations in the future. Now, what this really means is it opens the door to calculations in other light nuclei, and those calculations are really complement other methods because they might struggle to go into heavier nuclei. But additionally, we can provide results for potentials that have an extremely hard core, as it's not really a big deal for us. We can also provide results for local potentials and hopefully provide results that haven't been computed yet. And then as of recently, there's renewed interest in unbound isospin 0 states in helium-4 because there was a new puzzling experimental result. So there's renewed interest to be able to compute the system and have a better understanding. And then eventually what we'd like to be able to do is compute electromagnetic and weak capture reactions where it's of mainly astrophysical interest. But really what we want to do in the future is to be able to compute reactions with nuclear rearrangement. Now, if we could do this, this would be really a pinnacle achievement for our understanding of these systems and our ability to model them. Now, if we could do all of these things, then we'd be able to feed back those Norfolk chiral interactions and hopefully improve them and eventually get even better calculations done and better understanding of the system. And so with that, I'd like to thank you for listening and thank you for joining me.
And you're muted, I think.
Yeah.
I just yeah. So yeah. Sorry about that. I had some truck activity outside here. Thank you, Abe, for the nice talk.
Mm-hmm.
So now we have time for public questions. So if anyone has questions they like to ask, you can raise your hand, or I guess you could use the chat too if you like.
Patrick has a question. Go ahead.
Oh yeah, Patrick.
Yeah, thanks, Abe. Great talk. I had a quick question, which is you talked about the fact that you sort of have this, at one point you said sort of 1 MeV range where this approximation is valid, right? Oh, if you go more than about an MeV from the calculated energy, it doesn't really work very well.
Yeah, yeah.
What's sort of setting that scale? Like, why is it an MeV? Why is it not 100 keV or 10 MeV or something?
Yeah, so I think it changes quite a lot in the system, but really what you can think of is small changes in the so the nuclear potential has this massive well depth, and then as we change the boundary condition, we're really changing that in total calculation of the energy of the system is really just small changes in that. And so if you get past, like, my guess is probably more than like 10% of the well depth of the nuclear interaction, you're probably not doing very much. So you can actually do this if you just carry out you can do a toy model of this problem and do a square well potential and then measure these actually how good the fixed interior wave is doing. I did that in a toy case, but I couldn't really make any good enough figures for it. But I'd be happy to show them if you'd want to see it.
Okay, so and do you mean the NN potential well or the sort of mean field potential well? Say that.
Yeah, so I would definitely have to say the NN potential in that case.
For small nuclei like this, there's not that much difference.
Let's see, other questions? I don't believe I see any hands up. Or I guess probably most of the committee is saving their questions for the closed door portion, but if there's ones that people feel like asking now, that also works. Don't see any hands up, so perhaps at this point can thank Abe again for the talk and invite the public to exit so that the committee can talk to Abe a little bit by himself. So thanks everyone for joining.
Thank you.